Hello again. We are moving ahead in our discussion of differential calculus, and today we're going to talk about stationary points. This is lesson 12.8, so let's get started. Our definition of what a stationary point is, it's just any point where the first derivative is equal to 0 after I plug in that x. It can be a maximum, so it can look like that. So you can see that that tangent line that I've drawn has a slope of 0, which is what the derivative is. It can be a minimum. There you see another curve with a tangent line of slope 0. Or it can be what we call a horizontal inflection point. And there you see two examples of curves that kind of level off for a bit and then move further in the same direction. Either it goes down and stops and keeps going down, or it goes up and stops and then keeps going up. Either way, there's that moment there where it's got a tangent line that has slope 0. So those situations are the only ones that can be possible if you have a first derivative of 0, which means that the slope of the tangent line is 0. So how do I know which one it is, whether it's a minimum or a maximum? Well, you look at a sign diagram, and we talked about those in the last lesson. If the first derivative is positive before and negative after that point where the first derivative is 0, that means that the original function was increasing before and decreasing after that x value, and that can only mean that you have a maximum. If the first derivative is negative before and positive after, that means that the original function must have been decreasing before and increasing after, and that can only mean that you have a minimum. Now, if the first derivative has the same sign before and after, then you must have a horizontal inflection point, meaning that it was decreasing before and decreasing after, like this one on the left, or it was increasing before and continued to increase after, like the one on the right. So that's how you can tell, is by looking at a sign diagram. That'll tell you whether you have a maximum or a minimum or a horizontal inflection point. So here's an example. It's a tricky function to look at, but once we take the derivative, it becomes a lot nicer. It is 1/5 x to the 5th minus a half x to the 4th minus 8/3 x cubed plus 9x squared minus 9x. So if I take the derivative, you can see it looks a lot nicer. The derivative of 1/5 x to the 5th is just x to the 4th. The derivative of negative 1/2 x to the 4th is just negative 2x cubed. The derivative of negative 8/3 x cubed is just negative 8x squared. The derivative of 9x squared is 18x, and the derivative of negative 9x is negative 9. So I need to figure out where that's equal to 0, and if I do that, I can factor that out and get it x minus 1 times x minus 1 again, times x plus 3 times x minus 3. So what I will have is I have the first derivative equaling 0 whenever x is equal to negative 3 or positive 1 or positive 3. So I set up my number line and I put tick marks by those three numbers. Now here's what I'm going to do for the test values. I'm going to use the orange version of the derivative, and what that means is it's factored, so it's a lot easier for me to plug in numbers because I can figure out whether each factor is going to be positive or negative, and then I can figure out whether the entire thing is going to be positive or negative. Let me show you what I mean by that. I'm going to use a test point that's lower than negative 3. So let's say it was negative 4. If I plug that into the x minus 1 squared, well, that's being squared. So it really doesn't matter what I plug in, because whether it was positive or negative before I squared it, once I square it, it's positive. So that first thing, that x minus 1 squared, that's always going to be positive. Now if I take that negative 4 and I plug it into the x plus 3, I get negative 4 plus 3. Well, that's a negative 1. So that term is going to be negative. If I take that negative 4 and I plug it into x minus 3, I get negative 4 minus 3, which is negative 7. So altogether, I've got a positive something times a negative something times a negative something. And so that means a positive times a negative is positive. So the derivatives everywhere before x equals negative 3, they're all positive. Okay, now let's look at a point between negative 3 and 1, and this is a situation where I can use 0, and I love to use 0 if I can. So if I plug it into that first set of parentheses that's being squared, again, it's being squared. It's always going to be positive. But if I plug that 0 into the x plus 3, that's going to be 0 plus 3, which is now positive 3. And then if I plug 0 into 0 minus 3, that's still going to be negative 3. It's still a negative number. So I have a positive times a negative. That's a negative. So every derivative between negative 3 and 1 is going to be negative. Now I take the interval from 1 to 3 and I pick a value, let's say it's 2. I plug that 2 into that first term that's being squared. It's being squared, it's always positive. Take that 2, add it to 3, and I get 5. That's still positive. Take that 2 and subtract 3. That's a negative 1. That's still negative. So I still have a positive times a negative. That's still a negative. Now let's take a number that's bigger than 3. Let's try 4. Plug it into that first set of parentheses that's being squared. It will always be positive. 4 plus 3 in the second set of parentheses, that's a positive 7, so that remains positive. But now looking at the last set of parentheses, 4 minus 3, that's a positive 1, so now that's positive. So now everything's positive. A positive times a positive times a positive is positive. So I can see the first derivative is positive, and then negative, and then negative, and then positive. What that means is the original function is increasing, and then decreasing some more, and then increasing. So looking at negative 3, if the function is increasing before negative 3 and decreasing after, I must have a maximum there. And looking at x equals 1, it was decreasing before and it's decreasing after. So it's not a maximum, it's not a minimum, it is a horizontal point of inflection, which I've abbreviated with POI. And then lastly at 3, it was decreasing before and increasing after x equals 3, so that can only mean I have a minimum at x equals 3. So just to summarize, I have a maximum at x equals negative 3, I have a point of inflection at x equals 1, and I have a minimum at x equals 3. So that's how you find stationary points and classify them as a maximum, minimum, or a horizontal point of inflection. If you have any questions, please let me know, and I will see you tomorrow.